So the next talk is by Muhammad, and if I understood correctly, he will tell us about how safe Rust is not that safe after all.
Yeah. Hello. Yeah. Hello, everyone. I'm presenting counterexamples in safe Rust. So before I start breaking down these words, I'll start with this plot. This shows the distribution of bugs in Chromium. Wait, I'll try. Okay. I can hold it. Oh. Hello. Does this work? Okay. Yeah. So I'll start with this plot. This shows the distribution of bugs in Chromium. As you can see, 33% are like memory unsafety and 36.1% are use after free. So essentially 70% of the bugs are related to memory safety issues. Because of this, recently there has been a lot of push to switch to these memory safe languages. Even White House released this last year, and where they reminded that future software should be memory safe. And that's why memory safe languages like Rust has been like very popular. Yeah. So why is Rust used? Like compared to other languages, because Rust, like code written in Rust guarantees the same traditional performance like C and C++. It is memory safe, so there's no dangling pointer, there's no garbage collector, there's no use after free, and it also has type safety along with the memory safety. It's important to note that Rust also allows certain operations using the unsafe keyword. So when you use the unsafe keyword, compiler is like, okay, you're on your own. I hope you trust, you know what you are doing. I'm not going to interfere with that. So essentially, is Rust really memory safe? In unsafe code, the responsibility lies on the developer. But in the safe code, the responsibility is on the compiler. But in this talk, we're going to talk about just the safe portion and not on the unsafe part of the Rust. Okay, so we'll talk about 5 different attack patterns that break memory safety in safe Rust. And then we'll evaluate these attack patterns in the Rust ecosystem to see whether they exist in the Rust source code, whether the existing tools capture these attack patterns, and have these ever been exploited in the existing Rust CVEs. Okay, so here are 5 attack patterns. There are very simple things like file system access, command execution, build time effects, and some little complicated things like compiler unsoundness. So what do I mean by file system access? By file system access, we mean that just accessing any file in the system. So when file paths are like improperly handled or there is insufficient sanitization, it is possible to break memory safety. For instance, for those of you who are not familiar with Rust syntax, please ignore the code. I'll break it down. Okay, so if you have a const pointer, in any language you should not be able to modify it because const means const. But here, what this block of code does is it takes a const pointer and then it modifies it to store another value in it. So it does this using this special file proc self-mem. This file is present in Linux operating systems. It contains the map of the memory of the process. So essentially what happens is we go to that file, we look where this const pointer is stored in the memory, and we directly modify it. So as a result, let's say if it initially had 5, we can write it to have 10. And all of this is being done in safe Rust. This is not just limited to modifying const pointers. This can be exploited to do read and out-of-bound reads and writes. For that, consider this. This figure shows the layout of a Rust vector. A vector comprises of 3 different things. The first thing is a pointer. The pointer points to the buffer, and then there's a length and the capacity. So the Rust vector has this length and capacity stored because whenever you try to access, let's say, any certain index of a vector, like I want to see 10th index of the vector. So the compiler will dynamically check whether that index is in the bounds or not. It just inserts those checks in your code. So that's how it maintains the safety of the block. Because if that index is not within that capacity, it will just panic the code and exit so that there is no out-of-bounds access. So what we can do here is, let's say we take a vector as an input, we take an index and an element. Let's just assume this was our vector. of length 2 and of our capacity 4. And the user says, I want to write something to the 10th index. There's no 10th index on this. But I do know where this part is present, right? So I can just go 10 indexes ahead of this point and write something there using the same file. And after that, when I try to print the 10th index, this should be an error because the capacity, the 10 is greater than this capacity, and the compiler will panic. But this capacity is also stored in the same file. So here in this part, we can get to this thing, modify this to index +1, which will be 11 in our case. And if I try to print this now, this will perform an out-of-bound reads as well. Yeah. Okay. You can also do some bad things with command execution. Here there's Ferris. We can assume that Ferris likes apples here, so that's why he's happy. There's a Rust program that has a secure memory location. But you have an evil command function, right? So what this function does is, it spawns a new process. That process can attach to your existing Rust process. And it can modify the value that was stored in that secure memory location. And then it can detach and quit. We implement this as through GDP. Here, the GDP spawns a new process. It then attaches to the Rust process and then modifies the value and then quits. Please note that this is the only example that requires pseudo privileges, because you cannot modify memory in another process without having the pseudo privileges. But there are some certain Rust crits out there that do require pseudo privileges, so this is a possible attack vector. The next thing is compiler unsoundness. Okay, so sometimes compiler can wrongly assume that certain code is safe. We'll talk about lifetime. By lifetime, we mean the scope of a variable. So what we want to do is, we want to have a function where if I provided a variable with a lifetime a, let's say of this length, let's assume lifetimes are length in our case, right? Because it's a scope of a variable. So if my variable was initially valid for this duration, I want to make it valid for some other duration, that lifetime annotation b. This should not be possible, but this is possible in Rust because of the compiler guarantees. So if I try to make a function like this, I can have this helper function as a helper variable as an input. This double reference thing cannot exist in Rust unless a lives longer than b. Because if, let's say, a goes out of scope, then b is pointing somewhere and there is nothing here. So this will be a dangling reference. This is not something you can have in Rust. So for you to declare this variable, the lifetime of a must be greater than b. And we have another thing that's also lifetime a. And our return argument is a lifetime b, which is different than this lifetime a. So if a lives longer than b, then this means that a lives for all the duration b is valid. So hence compiler can say that, okay, because you gave me an a and you also told me about this thing, so I can assume that this same variable will be valid for lifetime b. There is nothing wrong in this code. But it is problematic if we can achieve this without this. Okay. So we have an evil function once again. We're going to build a wrapper around the previous function. This time we'll use something special. It's a static lifetime. By static lifetime, we mean that the variable is valid for the entire duration of the program. So what's going to happen here is, like here, there was a, b, and a, right? So this lifetime converter takes argument with a lifetime a, b, and a. So for this, because it was expecting to have an a and a b, but we gave it a static. Static is valid for the entire duration of the program. So static is bigger than a or b, or at least as big as any other a or b. So the function can call, okay, this is my b, this is my a, and this is a. Since both of these things are a, and this thing is b, this function wrongly assumes that this a is same as this a. They are both given the same annotation. And then it returns this variable with an annotation b. but our annotation was initially static. So what we did was we took something that had a limited lifetime and changed it into something that has an infinite lifetime, like for the entire duration of the program. And this can lead to dangling references. Okay, you can also do some things with build time effects. By build time effects, we mean that these are some certain configurations or optimizations that occur during the compilation of your source code. So for example, there's a user, and there's some certain library code he wants to run. That library has a build.rs file. That build.rs file is there to do some certain customizations or like some installations, etc. But for this, you call the REST compiler, but this is an evil file. So what this build.rs does is, this modifies this flow. We'll talk about how this flow is modified, such that user thinks the user will think that he is talking to the compiler. But no, user will be talking to our updated build.rs file, and this will execute your code through the compiler. That's the goal. So our initial is something like this, where user interacts with the compiler. What we want is the user interacts with our file, and that file interacts with the compiler. So we are essentially building a wrapper around the compiler. So user calls the compiler here, and then the library wrapper intercepts. It can do very bad things with this. For instance, it can, let's say I want to run this a.rs file with this compiler, right? So it's intercepted, the call is intercepted. It modifies it a.rs to add some like really bad code in there, which like maybe reads my private encryption keys or something. And then it runs that code. And then it restores the file. It can even restore timestamps. And as a result, the user thinks he was running a.rs, but no. The wrapper updated that a.rs, ran some other code, and then restored the file again. So for the user, the code that ran was what's in front of him, but what the code that was actually executed is something different. We implement this as a linked list library. So yeah, this is very much possible. Okay, environment variables configurations can be modified to perform various malicious tasks. For example, you can modify this path variable to set to some bad location. So whenever user runs an ls, it will execute some other binary, and you can place that binary through even your build.rs file. Okay, how do we evaluate this? For existing tools, we use 4 different symbols. The tick represents that tool successfully identifies the attack. The cross is like the tool fails. The tilde is tool like is ambiguous, or the tool does not support this. And the dash is that we are unable to run the tool. Okay, we obtain this table. It's very interesting to see that this proc_self mem examples, which are the first 2 examples I showed, it's not like supported by any of the tools out there. This cargo wrapper, this is the build.rs example. None of the tool captures this. Miri does well on those lifetime issues, but on generally, most of the tools are like missing or unsupported. So there seems to be a gap here. Okay, so we want to see whether these attack patterns even exist, right? So we take top 500 Rust crates by downloads. We also pick random 500 crates, and we also pick all the crates on RustSec. We use cargo scan here, which you heard about 2 talks ago, to filter this Rust code by side effects. And we'll look for these 4 side effects, and then we manually label these to see whether these code blocks follow those attack patterns or not. And we obtain this. This is a very high number in command execution. The example is, one interesting example is here. There is this crate that creates this executable file, and it executes it. It gives it the executable permissions, and with the later function it runs it. But here, this command name is it's a public function. Command name is going directly as it is in here, and so you can like sneak in any command in there and perform an arbitrary command execution. Okay, in Rust CVEs, there is grep CLI. This was a Windows vulnerability where it will look for executable in your local directory rather than global path, and that will lead to command execution. this inconceivable is a crate that was specifically designed to perform those build.rs attacks. And there's Rust decimal that also used environment variables and command execution. Okay, so based upon this, these are all the problems, right, I talked about. Our future direction is having two different solutions to this. We are building LHS. This is left-hand side. There's an interesting story to this, why it's called left-hand side. I'm happy to tell it later. Static analysis tool that catches these attack patterns. And the second is a cargo share log, where we are trying to formally model trust in supply chain of Rust packages. If anyone has any questions about this, I'll have to take it after the talk. I got acknowledge my professor, Dr. Stanford, for all the help. And yeah, the takeaway message is sometimes breaking things is the best way to keep them safe, because we hope that with all the problems we find in Rust, maybe it can become more secure in the future. Yeah, if anyone has any questions.
Yeah, so there's plenty of time.
So it's an interesting talk. I wonder, it seems like most of these issues, you could take Rust out and replace it with any other safe language. And it seems like the main point is maybe not about the safety of the language, it's about the other dependencies you have when working with a language, whether it's the compiler or the build system.
Yeah.
Is that fair?
Yeah, these are the interactions the language is having with the system. But the problem is that, the concern here is that whose responsibility it actually is to save this. Like, for example, if there's a code that's interacting with proc self-mem, is it the compiler responsibility, or is it the operating system responsibility? And there seems to be like, problem here. Who's gonna fix this?
I guess personally I would rule it as an operating system thing, but I guess we're an appeal crowd, so maybe it's a appeal responsibility.
Yeah, I kind of had like a similar comment. I guess it does seem like a lot of the things that you talked about are, I guess, like, I mean, you can classify them as like operating system security things. But I guess I do have one question, which is also related, but I'm like, a lot of these things don't seem exclusive to Rust. So I'm wondering if you have any plans maybe to have like a more general purpose static analyzer for other languages even, and not just Rust.
Currently, the static analysis plan is not for any general purpose, but this tool is currently is implemented for Rust, just for Rust packages. But in principle, this concept could work on all languages. What we are doing for this cargo share lock. Yeah.
Thanks.
More questions?
Since there's time, will you tell us a bit more about these future directions?
Sure. So, cargo share log is like formally modeling trust in supply chain of Rust packages. So what we do is, we like, when you like, for example, as a user, you go to crates.io and you see a certain crate. How do you decide that, oh, this is safe to use? Sometimes generally we look at the downloads, or we look at who wrote that crate and stuff like that. So this is just an attempt to like take all of those assumptions and formally model this through Z3. We use that metadata information. We also use side effects information from cargo scan. We also plan to integrate more static analysis tools in there. And like based upon all those informations, we want to have a solution to this problem, that what's the least weight assumption I'll have to make so that I can say that this certain crate is safe to use, or like this certain code is safe to use. Yeah.
Okay, thank you. So I think we don't have short talks, so we'll stop here and let's thank Muhammad again.